Hi everyone, we are from Group 3. Our project title is Development of an Interactive MATLAB GUI for Simulating Projectile Motion with Aerodynamic Drag. We have 6 members in the group. My name is Peter and my group members are Tan, Ong, Juliana, Rachel, and Aina. Our project is about projectile motion in real life. Projectile motion is a fundamental topic in physics and engineering, but real motion is affected by air resistance, which is often neglected in basic models. This simplification reduces accuracy and makes the concept harder to visualize. The project develops an interactive MATLAB GUI to simulate projectile motion with aerodynamic drag. The GUI allows users to change parameters and observe the motion visually. This helps improve understanding and connects theory with real-world behavior.
Hello everyone, I'm Aina Karida. So the objective of this project, firstly to formulate and solve the differential equations governing projectile motion under the influence of gravity and aerodynamic drag by applying appropriate numerical integration techniques. Secondly, to develop an interactive MATLAB graphical user interface, GUI, that allows users to adjust launch parameters such as initial velocity, launch angle, drag coefficient, and mass, and to visually observe their effects on projectile motion. Finally, to implement a file input or output system that records key simulation results, including projectile range, maximum height, and time-dependent position data, and export these results into external files such as TXT or CSV formats for further post-processing and analysis.
Hello everyone, my name is Ong Chusiang. Now I'll be walking you through the mathematical model behind our simulation. So our problem definition starts with the governing physical law. In a standard textbook problem, we usually assume a vacuum where only gravity acts on the object. However, for realistic simulation, we must account for air resistance, which is drag force. We model this using the quadratic drag equation shown here. The key takeaway is that drag is not constant. It depends on the square of the velocity. This means the faster the projectile moves, the harder the air pushes back, making the physics nonlinear and complex. Next, because drag always opposes the direction of motion, it changes direction as the projectile curves. So to handle this, we resolve the forces into horizontal x and vertical y components. In the horizontal direction, drag acts alone to slow the object down. In the vertical direction, drag combines with gravity. So by applying Newton's second law, which is the F equal to ma, to these components, we derive the specific acceleration equation which is ax and ay that drive our simulation. Finally, to solve the equations in our code, we use the Euler's method. Because of these equations are too complex for simple algebra, we use the Euler's method. This is a numerical approach where we calculate the position and velocity in tiny time steps, which is millisecond by millisecond, to accurately trace the projectile's path. So that's all for the problem definition. Thank you.
The methodology of this project is based on a structured computational workflow that integrates user interaction, numerical computation, visualization, and data management. The simulation process begins with user-defined input parameters entered through a MATLAB GUI. These inputs are then validated before being passed to a numerical solver that applies Euler method to compute the projectile motion under aerodynamic drag. The compute results are visualized in real time and can be exported for further analysis.
Hi, my name is Rachel Linda Janilon and I'm going to present about our project flowchart description. Our project simulation begins when the user runs the MATLAB function. After that, user need to input value for initial velocity, launch angle, drag coefficient, and projectile mass. After user input all the values, the program will check for invalid inputs. For example, negative mass, 0 or negative velocity, and either the angle is outside the valid range. Once the inputs are validated, the loop function will start to calculate the velocity magnitude and then evaluate the drag force, and lastly determine the accelerations in the x and y directions. All the results will be stored in arrays for plotting the graphs. This loop function will continue until the vertical position becomes 0 or negative. When loop ends, the projectile trajectory will be plotted. Users can observe and compare the plotted projectile trajectory with the ideal motion. After the simulation, users may choose either to export the simulation data or not. The data can be exported to text file or Excel file. The simulation ends when all results are displayed and user exits the GUI or resets the system for a new simulation. And this is our full flowchart logic.
Good day everyone, my name is Juliana binti Abbas. So now let's move on to the code implementation. So in this project, projectile motion with air resistance is simulated using a MATLAB function called projectile_Euler.m. So the function is the main calculation part of the system and is called by the GUI after the user enter the valid input. The motion is solved numerically using Euler method in both horizontal and vertical direction. The function takes 4 input, which are initial velocity, the launch angle, the mass of the projectile, and the drag coefficient. These parameters allow different launch of condition to be tested. The output include the horizontal and the vertical position array, the time array, the total range, and the maximum height. This modular design make the function is easy to use and connect to the GUI. Gravity and air density is defined first, and the projectile is assumed to be a spherical, so its cross-sectional area is calculated using a fixed radius. A small time step of 0.01 second is chosen to keep the numerical solution stable. The launch angle is converted into radian, and the initial horizontal and vertical velocity is calculated. Projectile start at the origin and the array prepared to store the result. The simulation run in a while loop as long as the projectile is above the ground. At each step, the magnitude velocity is calculated, followed by the drag force using a quadratic drag model. The drag force is split into a horizontal and vertical, and the Newton's second law is used to calculate the acceleration. The velocity and position are then updated using a Euler method. The simulation stops automatically when the projectile hit the ground to avoid unrealistic result. The horizontal range and maximum height is calculated from the stored data and sent back to the GUI for plotting and analysis. That's all from me. Thank you.
Hi everyone, my name is Tandishan. Now we're moving on to the result and discussion. We compare our simulation results against ideal vacuum conditions to analyze the effect of air resistance. First, let's look at the projectile trajectory. The red dashed line represents the ideal motion in a vacuum, while the blue solid line shows the actual motion with drag. As you can see, the air resistance caused the trajectory to become asymmetric, and it significantly reduced both the maximum height and the total range compared to the ideal case. Next is the velocity versus time graph. Unlike the ideal case where horizontal velocities stay constant, our results show a nonlinear decrease in speed. This happens because the drag force is proportional to the square of the velocity, and it causes the projectile to lose kinetic energy rapidly at the start. Similarly, the height versus time graph confirms that the air resistance limits the vertical motion. The projectile reached its peak earlier and returned to the ground faster. This results in a shorter total flight time compared to the ideal theoretical values. Finally, we validate the system functionality. We successfully implemented the data export feature, saving simulation results into text files. We verified that the export numerical data match the graphical outputs perfectly. This allows for further external analysis.
Last but not least, we'll conclude about our project. This project developed a MATLAB-based simulation to analyze projectile motion with gravity and aerodynamic drag using Newton's second law and Euler's method. The result shows that the air resistance reduced maximum height, range, and flight time, producing more realistic and asymmetric trajectories. An interactive MATLAB GUI allows users to adjust key parameters and visualize their effect clearly. The simulation also supports data export for further analysis. Overall, the project provides a useful educational tool for understanding realistic projectile motion.